Take it away, Mr. Nice Guy.
All right. Thank you. Thank you. The after lunch talks are always kind of tough because everyone had the great lunch and riding a nice sugar high. Then comes the sugar crash. And then a talk that's got something to do with something besides Alice Cooper sets in. But I came prepared. I have with me the undisputable best candy on the planet, York Peppermint Patties. But that's not all. They're pumpkin shaped. How much more can you ask for? So here's the deal. If you ask a great question during my talk, I will give you a York Peppermint Patty, which is cold, by the way, because it was in the cooler with my frozen water bottle, because DevOps is all about component reuse. So if you ask a great question, I will give you a York Peppermint Patty that will allow you to extend that sugar high just a little bit longer. So we're going to talk about the mean stack today. Specifically, we're going to talk about how we achieve fault tolerance, scalability, and performance out of it. And we're using the mean stack as a reference. Because if you haven't picked up on it, because the sugar buzz is already gone, MEAN is actually an acronym which stands for MongoDB, Express, Angular, and Node.js. So I'm going to define some terms here just because everyone has a little bit different definition of them, and this way we can all be on the same page. Fault tolerance, we're going to define today as the ability to survive failures at the application, the stack, and the hardware level. And we're going to define scalability as the ability to easily expand and shrink our stack to meet demand. And then finally, we're going to define performance as our ability to serve our clients within defined metrics. Is everybody cool with that? All right. That was kind of weak. That was really weak. Incoming. Nice. Somebody's paying attention. So what we're not going to cover today, we're not going to do a deep code dive because we're talking about 4 different technologies and we've got people of different skill sets in here. So to try and talk about the actual code of how we pulled all this off would be boring to people who are experienced with this type of environment and be bewildering to people who are just being introduced into it. So instead, we're going to focus on how or on why we do it. Why we're choosing these components, why we're placing them, where we place them, and why we're doing the things we do so that at the end of this talk, everyone walks out of here with the ability and the knowledge to apply these same principles to your environment no matter what stack you're running on. So you may wonder why I chose to do this talk on the mean stack instead of choosing something like Cassandra, React, the AWS API Gateway, and Python. Well, some of you may have picked up that that's a horrible acronym, so that's kind of a non-starter there, especially if you're fond of any of those technologies. But it turns out there's a second, possibly more relevant reason as well. Whenever you choose the mean stack, you're choosing 4 different technologies that are already assembled together for you. It takes a lot of work and effort to get all of them to play nicely together, and so by choosing the stack, you're getting that groundwork done for you for free. And now if you've ever used a stack technology before, you know there's a downside as well. For example, when you assemble 4 different components like this and intend for a bunch of different people to use them in a bunch of different use cases, you have to make certain assumptions for them. And so those assumptions may be in direct conflict with your business application, which would make the stack a non-starter. Additionally, you run into scaling issues. While a given stack may run well under a few thousand users, it may really start to come apart at the seams under hundreds of thousands of users. And those are 2 pretty big negative reasons, so you got to be wondering, why would you choose a stack ever at all? And the reason is this. I work with a lot of early stage tech startups, and 99% of the time, the product that they originally launch is not the product that someone actually ends up giving them money for. And so by choosing a stack such as the mean stack, it allows you to start writing the business application logic on day one instead of writing framework code on day one, which is going to allow you to build your MVP or your minimum viable product faster, get it out in front of your customer sooner, and get their feedback so that you can actually know what someone is willing to give you cold hard cash for, which is key in a startup. All right. So there was a time I would have skipped this slide entirely because everyone knows what high availability is, right? But I've worked with people in the past who honestly believed, not that they were malicious, just that they really believed that once they pushed their code into production, they were done with it. 5 nines availability was guaranteed. I mean, we can even install an NPM package called Forever. What more do you need besides a package called Forever to keep your app running forever? Well, it turns out there's a little bit more to that, and I'll tell you a story about my parents. Love them to death, but they will click on the Internet Explorer icon on their desktop, which takes them to their home page of Bing, and then in the Bing search box, they'll type Google, and then click on the link for Google so that they can Google something. So the point I'm trying to make is never, ever, no matter how bulletproof, rock solid your code is, never underestimate the power of the end user to do something you never thought of. Sometimes it's something funny, like the story about my parents. Sometimes it's something devastating that results in your whole stack of servers coming crashing to the ground. So the point is, high availability is fought for 9 by 9, day by day, hour by hour, and it's never to be taken for granted. So let's jump into building our environment. We're going to start with our node server that's going to be running our Express and Angular app on it. And so as long as Node's sitting there running, everything's working fine, right? But we instantly lose our performance and our fault tolerance the minute that Node process crashes. So we can actually use a package from the process supervisor class called PM2. PM2 is going to sit on top of the server and watch the Node process, and when it sees that Node process not there, it can restart it for us. So now we've gained a little bit of fault tolerance out of that because our Node process can crash and it's going to get restarted automatically without us having to do anything. The other thing PM2 brings with us is most servers have multiple CPUs on them, but Node's single-threaded. So we're letting hardware sit there and go to waste. Well, with PM2, it ties into the clustering support built into Node.js, and it'll help us cluster our app so that we can run a separate Node process on each processor in this server. So now we've got fault tolerance, and we get a little bit of scalability there because we can serve multiple requests, and we get some performance benefits as well because whenever one of those Node processes dies, we can still service client requests because the others are going to pick up the slack while PM2 goes and spins up a new process to replace the one that died. So we're just roughly 10 minutes into the talk here, and we've covered fault tolerance, performance, and scalability, right? Right, sweet. It's your peppermint patty time. Well, that's all assuming that that server never dies, because there's no chance that a sysadmin would ever reboot your server, right? Right. Rumor has it that those guys actually enjoy rebooting your production servers, especially when they know it's the only one. So what can we do? Could add multiple servers, right? If we have multiple Node servers, then we can reboot one and we'll still be available. But then the question comes up, how are we going to route requests in between them? Well, if we're running in AWS, we can use an elastic load balancer, put that in front of our servers, and it's going to balance the traffic across all of our Node servers. If you're running in your own data center, you can accomplish the same thing using HA proxy. The cool thing about this is we can enable health checks as well. So now our load balancer can check each Node server, and whenever that server fails the health check, it'll automatically remove it from the pool rather than waiting for us to figure it out because we're getting flooded with phone calls from pissed off customers. We also gain a little bit of benefit in performance because we can terminate our SSL certificates on the load balancer. This shifts the workload of managing the SSL off to the load balancer instead of having to handle it on our application servers themselves. Well, we've gone that far. We've got multiple servers. So it's time to add in something for security. And though security doesn't directly relate to our 3 goals of fault tolerance, performance, and scalability, it kind of does whenever you get hacked. Got that going for you, which is nice. So in Amazon, if you're not using VPC, all of your servers are publicly routable, meaning anyone can drive by and launch an attack on them. And you can defend against that with your operating system firewall, which is kind of cool, but I hate wasting hardware. And to me, it's wasted hardware if I have to spend CPU cycles defending an attack from someone that I don't even want there in the first place. So we can use a VPC. It's a virtual private cloud. And using the VPC, we can define security rules saying that the only traffic allowed into our load balancer is on ports 80 and 443. And the only thing that's allowed to talk to our node servers is the elastic load balancer. And so we add this extra layer of protection around it. So we're still going to get drive-by attacks, but they're going to happen outside on the VPC, which gives us an extra layer of security before we have to actually worry about them. Well, since we've gone far enough to add multiple servers and put it in a VPC, we can add in availability zones as well. All right, so everyone who's familiar with AWS know that when you launch something into AWS, you launch it into a region, whether that region is US East, US West, Singapore, whatever all the other regions are. But then when you get inside of that region, you start seeing these availability zone things, and it starts asking you about those. Well, in a region in AWS, an availability zone represents a physical data center. It has its own internet supply, it has its own power supply, it has its own water supply, and it's physically isolated from the other data centers in that region, but close enough that you can still make low latency communications across those availability zones. So by putting each server into a different availability zone, we now have the ability to not only survive a failure at the node process level, but we can also lose a node server completely, and we can even sit back and watch an entire AWS data center go down in flames and our app remains highly available. So it would be a bummer to see that actually happen, but it would be good to know that our app is going to ride through that without issue, right? Right. Who needs peppermint patties? All right, incoming. Anyone? Yeah, here we go. This is probably a great opportunity to point out that I'm in DevOps and not Major League Baseball for a very specific reason. Some of you might be figuring that reason out. For those of you who haven't, you can think it over while we install our MongoDB servers. So you can see I've put in 3 MongoDB servers, 1 in each availability zone, just like our node servers. But what you may be thinking is, there's no load balancer in front of them. So how are we going to load balance the traffic across 3 servers with no load balancer? Well, Mongo is actually going to handle that for us. When you put in 3 servers, you can put them in what's called a replica set in Mongo. And when Mongo servers that are members of the same replica set see each other, they hold an election, and they elect one as the master. And that master is the only one who's allowed to write data. So all the writes will go to the master, and then the secondary servers will read from the master to get the updated content. So that sounds like a lot of work for us, but it's really not, because all we have to do to take advantage of that from our node server is in our connection string, just list all 3 servers. And then the driver figures out who the master is from there. So again, I hate wasting hardware, so it seems kind of wasteful to have 3 node servers, but we can only write to one of them. and the others are there just in case. So we can also enable secondary read preference. Now what secondary read preference does is that allows us to state that if our query for the MongoDB server is a read query, it can go to any server. And so Mongo, the driver, will figure out the closest server. So now we've got some scalability and performance improvements there because we're not bottlenecked onto a single server for our reads and writes, and we can survive multiple failures because if one of those servers fails, the others will pick up the slack, and if that server that fails is the master, they'll hold a new election and pick a new master. If we need to scale that even further, we're going to look at the types of database activities that we're seeing. If we're seeing a large number of read operations, adding additional servers to our replica set will increase the available pool of servers we can read from. If we're seeing a large number of write operations, we can do what's called sharding. And sharding allows you to segment your data so that each one can be a subset and each one can have its own master, so you get multiple places to write your data. The best way to explain that is a scenario where you have a global application where we have servers in China, the United States, and Europe. So if you're a user in China and you update, say, your user profile information, and that has to go from China to the United States to update the master, and then wait for a secondary server in China to come replicate that content, it can make for a pretty poor user experience. But user data is something that we can identify as geographically isolatable, right? Because odds are most of our users from China aren't going to be in the United States or Europe logging in. And if they are, it's because they're on vacation and we can't really help that. But most of the time, they're going to be in that area. So we could define our data by geography so that the Chinese user accounts are in China, the US user accounts are in the US, and the European user accounts are in Europe. But then all the other data in the database is replicated across all of them. Does that make sense? Yep. Awesome. So it's important to understand that that is not something that's specific to MongoDB. All of your major database platforms have similar strategies for dealing with that type of scenario, the replication and the sharding data. It's important to understand how each one of them deals with it, though, because the rules that Cassandra uses are different than the rules that MongoDB uses, which is different than the rules that CouchDB use. And each of those have good and bad scenarios where they are the preferred database choice for that type of application. And I've got a link on a slide here at the end that has a really quick, like 10-minute read that goes through all the database platforms and gives you like the pros and cons of each one. So if you're not familiar with it, you can use that link and figure it out. So we talked a lot about how to achieve fault tolerance and scalability. What we haven't talked about is money, because fault tolerance and scalability and performance is cool unless you can't afford it, right? So it's important to know how much things cost in hosted environments like AWS. So let's use our demo application here where we've got an elastic load balancer, 3 Node.js servers, and 3 MongoDB servers. And let's kind of see what that's going to cost us. If we scale each of our instances as T2 mediums, which will give us 2 CPUs and 4 gig of RAM per server, those run you about $40 a month in AWS. The elastic load balancer will set you back another $20 a month. So all total, that's $260 a month. We still have some data, because we'll have some data storage needs, but data storage in AWS is 8 to 10 cents per gig, so we can actually store quite a bit of data and still keep under the $300 a month mark, right? Sugar Buzz is wearing off. Really? Is there a guy that can hook me up? So that's cool. So we have these servers and we know how much it's going to cost, but how many users is that going to support? 4. All right, that's not bad. 4 users for $300. No, I'm just kidding. So this is one of those questions where the answer really comes down to the thing you hate hearing most and the answer that developers love giving the most in every question ever asked. It depends on your architecture and your scalability and the way you designed your app. And it's true, but we can do a little better than that, right? I have done that exact application many, many, many times, and I can tell you that under the worst possible scenario, you should be pushing 500 to 1,000 requests per minute through there. If you're not, it's a sign to look at your code, not to look at your architecture. So how much faster you can get than that is all up to you. But this is a baseline so that you know whether you're doing well or you're not doing so well. Right on?
So this is for just the writes.
What's that?
Is this for the writes to the MongoDB?
This is through the whole thing, through the load balancer, through the node servers, into MongoDB, and back out.
Mostly writes to the MongoDB database? Or
No, it wouldn't be necessarily mostly writes. We're gonna measure that at the load balancer, so it's the number of requests coming into the load balancer. So they may be writes to the database, but they may be read queries to the database as well. So hopefully if things go well, we're going to have to scale that to support even more users someday. So let's talk about some ways we can approach that. We already talked about how to scale our database. For scaling read operations, we're going to add more servers to the replica set. For more write capacity, we're going to shard the database into segments. For our node servers, we can either add more node servers or we can add bigger node servers. Which you do is going to be dependent on your load testing results. Because different applications, even though they should all hit that baseline 500 to 1,000 number, some of them are going to behave better with more memory available to them. Some of them are going to behave better with more processes running, and your load testing is really going to be the answer to that. Another thing we can do is introduce a content delivery network, or a CDN. This is going to allow you to move your static assets, which are your images, your CSS files, your JavaScript files, push those off onto a CDN network, and we get a couple of benefits out of that. One, the CDN is usually closer to your clients than your own application servers are, so they're going to get a better response with that content coming from a server closer to them. The other is your node servers are now no longer having to serve up that content, so they're free to serve more client requests because that workload has been offloaded to them. We can also introduce an index server, whether you want to use Elasticsearch, Solr, Memcached, Redis, Lucene, any of them for the similar goal. And what you do is when your clients are querying your website, you want to send them to the search server because the search index server is going to be much faster than doing a generic query to your database. So you'll hit the search index, you'll find the record that your clients are looking for, and then you'll query the database server for that specific record, rather than doing a generic query to the database server, bringing all those results back into the app server, and then iterating through them one at a time, finding which one you need. So that's the basics of performance, scaling, and high availability. The big question now is, how do you know which to do? Or how do you know where to grow and when to grow? And monitoring is the answer to that. So I recommend everyone monitor everything on this screen for every server you own. Most people are pretty good about hitting the top ones. The two that people miss the most are CPU wait and CPU steal. So now CPU wait is the time your CPU is tied up because it's waiting for something else. The most common example of that is your hard drive. Your hard drive, even if you have the super fast, state-of-the-art SSD hard drives, is much, much slower than accessing memory or accessing data in memory. So the time that it takes for the CPU to request data, for the request to make it down to the hard drives to find the data, to push it back through the motherboard, to buffer it in the CPU, and it's finally available to the CPU, your CPU is tied up and can't do anything. And that's called CPU wait time, and CPU wait is how you'll see it on utilization graphs. CPU steal is specific to VMs. And so CPU steal For a VM, you have your virtual host underneath, and then you provision your VMs on top of that, right? Well, there's absolutely nothing on the face of the earth to stop you from provisioning more VMs than you have CPUs on that virtual host. As a matter of fact, it's common practice to do so. And so what happens is whenever some of the other VMs on that host start getting heavy CPU utilization, the virtual host has to pull those resources from somewhere, and it's going to pull it from your VM. Now, a lot of times there's nothing you can do about it, but knowing that that's what's impacting your application is key. And that's tracked on your CPU utilization graphs and identified as CPU steal time. Monitoring at our load balancer, we're going to monitor our 200, 400, and 500 requests. The 200 requests in this first chart here, that's the one you're going to look at to hit your 500 to 1,000 requests per minute. Those are successful HTTP requests to your load balancer. 400s indicate that someone was looking for something on your site that doesn't exist. Think of a 404 page not found error. And 500s indicate that the user asked your web server to do something that it doesn't know how to do, and it generated an error. Our unhealthy host count, we've already established that I hate paying for stuff that I can't use. So unhealthy hosts is a server that's gone offline, is no longer in the load balancer. And then finally, average latency. This is a response time of your load balancer to those requests. And it's just something you want to keep an eye on. Everyone's going to have a different goal of what good or bad for that number is. But the important thing is to measure and monitor that number so you know when you're hitting it and when you're not. All right, monitoring our database. Specific to MongoDB, we have the oplog window. So we established that the master does all the writes, and then the secondaries read from the master to get their replicated content, right? The way that works is MongoDB master writes to an oplog collection, which is a statically sized collection. And it just starts writing into it incrementally. And then when it gets to the bottom, it starts back at the top, just overwriting all the entries. So the time between the oldest entry and the newest entry in that oplog is your oplog window. That means that any server that goes offline has that amount of time to get back online, or it's the record or the data that it needs to catch up is no longer available. In this scenario here, we have 83 hours. So it's not something that's like minutes most of the time. It's usually quite a bit of time. It's different based on your environment, but it's a number that you need to know it exists. The ops counters, this is how we're going to determine how to scale. That will show you the operations on your database as far as the number of read operations, write operations, inserts, deletes, that type of stuff, and that's going to help you decide whether you can address your performance concerns through adding additional secondaries, or you need to shard to add additional write capacity. And then skipping down to the lower right-hand graph there, the global lock percent. Whenever Mongo does a write, it has to lock a certain portion of the database. While that's locked, nothing else can access it, which may cause things to queue up. That's represented in the global lock percent. And so it's just a good thing to keep an eye on so that as you see your lock ratio increasing, you know that things are bottlenecking there, and it's time to look at how your data is organized. And then the one in the middle, page faults. This is the death of Mongo. Mongo likes to have the working set in memory. It doesn't have to have the entire database in memory, but the set that it's working on has to be in memory for it to be performant. Anytime that the data Mongo is working on is not in memory and it has to go to the hard disk for it, it registers that as a page fault, and you'll see it on this graph. That's the first indicator that your Mongo performance is about to just fall off the edge. Good ways to address that are either break your data up across multiple replica sets or increase the available memory on your MongoDB servers. All right, takeaways. So know your goal. Are you building an MVP, a minimum viable product? Or are you building a roadworthy, high availability production application? And it's important to know what you're building because the steps that you take will differ. You're not going to throw the same amount of time, resources, and money into an MVP as you will an established application. So you need to approach the problem differently. Monitoring, I think everything today has touched on monitoring a little bit and the importance of it. If you have a problem, it's too late to start monitoring because you can't see what before and after was. So monitor everything from the beginning. Even if you don't think you need it, it'll come in handy sooner or later, and it's going to tell you where the problems lie, and it's more importantly going to tell you when the things that you're trying to do are making the problem better or worse. Load testing super important so you have a baseline. Without a load test to understand where your application's performance limits are, you'll get numbers from your monitoring, but are they good or are they bad? You don't really know because you don't have anything to compare them against. And then forecasting expenses, especially for those of you working for startups. Control all your costs. It's easy to do and make all your hardware work for you. So that's all the slides I have for you. The last one here has links to the mean stack itself, the different components that make it up, and then the link that I promised you on the database performance characteristics for each of the major database platforms. And my contact info, feel free to reach out to me at any point, at any time, for anything. I would love to hear from you. And thank you guys so much for coming out today. I hope it's been as enjoyable for you as it was for me. And we've got some time left, and I have a bunch of candy left, so who's got questions? Anyone? Nothing? Should I just throw candy out at random?
On the HBase there.
What's that?
I haven't seen a comparison on the HBase. Sandra, Mongo, how
Yeah. Do we need an acronym for that?
So you use the ELV, is it available for multiple zones, or if the ELV zone goes down, then it can't reach any of the other?
ELBs, elastic load balancers in Amazon, are automatically available across multiple availability zones.
So if one goes down, the ELV's still up in another zone?
Right. Yep. Comes for free. Well, not for free. It's what you get for your $20 a month. What else? Yeah.
Suggested load testing tools for the mean stack.
So, again, not in Major League Baseball. Loader.io is really simple to use. The free tests are kind of weak just because they're in limited capacity, but for $100, you get some pretty decent bandwidth as far as testing. And the way I usually do it is I'll batch all my load testing up, pay the $100 for that month, load test everything, and then cancel my subscription. Right? I can't imagine I'm the only one doing that, so. Another one, sorry.
Very well. And how you compare that with JMeter, which is open source?
Yeah, you can use JMeter as well. That was the other one I was going to bring up. JMeter is super powerful and covers like every possible scenario you could ever want. You just have to spend some time up front to learn how to use JMeter, which is not like, horrible. It's just something else to do during your day. Way to call me out. Yeah.
So let's say that your availability zone goes down for your master MongoDB.
Right?
You said that the other MongoDB instances will automatically, one of them will become master.
Right. Yeah, Mongo's kind of cool about that. The way it does its replica sets is the master's not allowed to say that he's the master. He can only be told that he's the master. And the reason they do it that way is because you imagine a scenario where you have one server in each availability zone, and let's say our master's in availability zone A, and availability zone A loses its internet connection. So now B and C are going to go, oh, we need a new master, and they'll elect new master, and they'll start writing data. But meanwhile, A is still up. He doesn't know he's lost internet connection, so he still thinks he's the master. And so when service is restored, there will be some confusion because each thought they were the master. So the way Mongo does it is the master is not allowed to say he's the master. He gets told every 30 seconds by the replicas or the secondaries that he's the master. And so when the secondaries that can't talk to the master anymore, they force a new election. And when the master likewise doesn't hear from the secondaries anymore, he doesn't think he's the master either and kind of falls into a stale state.
Have you found that there's any data corruption when you're using sharding?
I personally haven't had any problems with sharding resulting from data corruption. I've had tons of problems from sharding where you think you understand the business case, and so you shard the data, and then after you shard the data, you see the servers doing things you didn't expect because people are actually using the data differently, which meant that you sharded it on a bad key.
And sharding also kind of weaponizes the data. You don't really know what the access is. So sharding pieces, reconstructing it becomes much more difficult because you don't have one particular model. Whereas the data it's truncated data coming out of the data set. It's going across all the sharding instances.
Yeah, once you shard, it's kind of like a jigsaw puzzle, but you don't know what the end puzzle looks like. And you still have to put it together. Yeah.
A couple more questions. And one regarding, you have any recommended tool for monitoring hopefully open source applications?
Zabbix.
Sun also.
Sun has an open source tool? Right on. Nagios is another very popular one with lots of support and lots of plugins. If you're running in AWS, CloudWatch support is available, or writing to CloudWatch is available, and there's like different tiers for that. Some free, some paid. Right.
And my second question is, in our case, we have to use structured data. So backend, we have to use PostgreSQL, especially for its spatial capability. So would the architecture and for the scalability and all this stuff will be similar, more or less?
Yeah, it would be similar. Postgres has its own unique ways of scaling out, and I don't know that Postgres actually has like a sharding concept or not, but they do have scaling and replication.
So would you consider sharding the same as partitioning?
Yes. Yeah. Any other questions? Anybody else need candy? Is that candy? Yes, raise hand for a candy or question.
If you had a machine fall asleep for more than 80 hours, would you have?
Oh, so in the oplog window? Yeah, so his question is, in our oplog graph, we show that we had 80 hours for a secondary to catch up. What happens if you can't get it back up in over 80 hours? The short answer is you delete the data directory on that server, rejoin it to the replica set, and it says, oh shit, I don't have anything, so it just pulls the whole database over. And that's another concept to use if you're at 76, 77, 78 hours into it. I would probably do the same thing and just nuke the data directory rather than to try to have it read, 80 hours of transaction logs.
So you don't have, MongoDB doesn't have the concept of like copy from table and you give it time range and not have to meet up repeat everything?
No, as far as replica sets are concerned, it does not. It's either going to manage it completely without you intervening, or you can delete all the data and have it start from scratch.
Are those elastic searches that are on each one of your node processes? Are they completely separate from each other?
No, that was probably a poor choice of drawing it out on my part. I would do a standalone Elasticsearch cluster that gives you its own measure of performance and fault tolerance, and then have all the node servers communicate to it.
When would you use Elasticsearch over just treating your indexes? Like what's the line between
I would, in a perfect world, I would tune the indexes first and then add searching. Certain scenarios where you know, you're expecting a 100x increase in your everyday activity. You know, you're not going to be able to tune for that ahead of time. And so in a scenario like that, I would stand up the Elasticsearch cluster and let it act as the shock absorber for that load, and then tune my databases after the fact. But that's just my guess. I'm sure there's other ways.
One more question.
All right.
Scott?
If you're, and maybe this was asked already, if you're sharding by availability zone, do you run some risks of data loss there, right? Like you talked about sharding by geography, but if you're doing that and associating your partitions with specific availability zones, essentially, right? Do you run the risk of data loss, right, when and if that zone goes down?
Right. Not if each of your shards is a replica set on its own. So you don't have to have it as a replica set, but it's highly recommended. So then you've got redundancy and fault tolerance in that zone to cover that.
Across the availability zones.
Or even inside a single availability zone, just somewhere in that shard, you want a replica set, so that there's not a single server in there that has all of your data. All right, cool. Thank you guys so much. Enjoy the rest of the conference.